We introduced LOTUS, a novel approach for learning to optimize task-based ultrasound representations. Ultrasound imaging is widely used in many clinical applications due to its non-invasiveness and real-time capability. Moreover, precise segmentations can improve organs visualization and size measurement. However, ultrasound segmentation is challenging due to factors like limited resolution and contrast and imaging artifacts. As a result, there is general lack of data with ground truth labels which can be used for training. Modalities such as CT offer a higher resolution, standardized image formats, and calibrated intensities, allowing for improved organ boundary delineation. CT has therefore been extensively annotated and offers large datasets which are publicly available. Ultrasound simulators can generate ultrasound-like images from CT label maps to overcome the scarcity of training data. They mimic real ultrasound images by simulating the physics of ultrasound image formation. However, models trained on simulations fail when applied to real data due to the domain gap. This issue has been addressed in recent works where an intermediate representation image between CT and ultrasound has been proposed. This IR was then used to train a segmentation task in that image space. First, a large set of IRs is generated and used as a training set for segmentation task, with the CT label serving as for supervision. As an additional step, an image-to-image network is trained to close the domain gap. However, this IR is statically configured and only defined for one task. Moreover, each component was trained separately, which is limiting the application of this method. We propose to optimize the intermediate representations to adapt to different tasks. Unlike previous methods, we model a fully differentiable ultrasound renderer that updates the parameters guided by a downstream segmentation task. The image style transfer network is trained between real and task-based images, and additionally we use an identity-rendered image for better segmentation results. We train both networks simultaneously, achieving an end-to-end training pipeline. We first introduced the differentiable ultrasound renderer pipeline. We model ultrasound waves as rays propagating through tissues based on known mathematical formulations. Input to the renderer is a 2D label map with tissue labels. Each tissue label has assigned 5 parameters defining ultrasound properties. We use these parameters to define 3 submaps: attenuation, reflection, and scatter maps. The final ultrasound simulated image is constructed based on those 3 submaps. Next, we show how we optimize those ultrasound simulations. We show optimized image representations for 5 downstream segmentation tasks: vessels, kidney, spine, and liver. For each downstream task, the training data is generated on the fly and a separate segmentation network is trained. We start by rendering the images with default parameters, and then show how the images change during the training, producing an optimized image based on each downstream task. We show further examples of default versus optimized image representations. It can be observed that the spine, kidney, and liver appear brighter, while vessels darken and small organs around disappear. We construct our pipeline in an end-to-end training setting. We train a style transfer network between real and rendered images to account for the domain gap. We utilize an unpaired and unsupervised network using a contrastive learning scheme, where the generator learns to translate images into the target's appearance using adversarial and contrastive losses. We train both networks simultaneously in an end-to-end training setting. Additionally, we use the training image output, identity image output from the generator as an input to the segmentation network. This produces better segmentation results as it learns from a distribution consistent with the reconstructed ultrasound. We perform both quantitative and qualitative experiments. We compare the performance of LOTUS against fully supervised approach and against the frozen renderer with default parameters. LOTUS achieves higher dye score and lower Hausdorff distance for aorta segmentation and gives the best dye score for vessel segmentation. We show qualitative results during inference for the task of vessel segmentation. The real ultrasound image is first translated to the optimized ultrasound image appearance, learned during the training for the task of vessel segmentation, and then it's passed through the segmentation network to achieve the final segmentation result. Thanks for watching.